A very good day to lecturer. My name is Ting and today our group will give a short presentation about our group assignment, which is the instrumentation system for the measurement of temperature. So let me introduce my team member, which are Elaine Ha, Jinnie, Vincent Yuan, and also myself, Ting. And all the metric number is stated on the side. There are total 4 topics in our group presentation. The topic 1 is thermistor sensor background study. The topic 2 is instrumentation system design. And the topic 3 is explanation how the system working. And the last topic is functionality demonstration. Without any further ado, let us move to our first topic, which is thermistor sensor background study. The word thermistor is a combination of the word thermal and also resistant, because thermistor is a temperature sensor and is based on the principle of temperature depend resistant. And due to this principle, thermistor can be used for a lot of applications. And there are 2 common types of thermistor, which are negative temperature coefficient thermistor and also positive temperature coefficient thermistor. The NTC thermistor means that the resistance will decrease when temperature increase, and the relationship between resistance and temperature is nonlinear, where the change in resistance is huge when the temperature is low. And for the PTC thermistor, it means that the resistance will increase when temperature is also increased, and it happens rapidly in a short time, and it will cause significant change of the current. Thermistors are widely used in the part of system, industry, and also technology, like home application, medical equipment, automotive system, and climate control system. In our project, we will also use an electrical circuit to supply voltage toward the thermistor, and the thermistor will detect the temperature and change to another form of signal toward the signal condition, like non-inverting OM and also comparator. So let us move toward the historical part. The first concept of the thermistor is observed by Michael Faraday, who is a British scientist in 19th century, and the thermistor became common use in manufacturing in year 1940. In 1950, NTC thermistor and also PTC thermistor were developed, and NTC thermistor are used in temperature sensor, and PTC thermistor are used in self-resetting temperature switch. Glass bead thermistor were present in 1960, and the next decade of thermistor is cheap thermistor because it has a very low cost and suitable for public.
Thank you, Samuel, for introducing the background of the thermistor. And now we have to introduce about the instrumentation system design. And now we can see that the design of the housing of the electronic enclosure, the dimension of the housing is the length 185.5 millimeters times width 50 millimeters and times the height of the casing 72.5 millimeters. The thickness of the wall is 3 mm for each side, and the total height including the handle is 158 millimeters. Next, we can see that the design cover of the electronic enclosure, the dimension of the cover for the length is 185.5 millimeters times the width 50 millimeters and the height 10 millimeters. The thickness of the wall also 3 mm for each side, and it can be seen for the front view, top view, and the right view. For the final design of the electronic enclosure, we can see that the figure shown below is the assembly of the casing for the design, and all the component is placed inside the casing. The figure shows the final product of the casing that we use to measure the temperature. After that, we can see the daily use for our instrument. The power supply is plugged behind the casing and used as the portable temperature measurement. It can be used to measure the air temperature and also the water temperature. And the last, the systematic diagram is shown as below, and it will be introduced by Jinnie. Thank you very much.
Now I'm going to explain how our instrumentation system works. From the broad diagram shown above, it can be said that the temperature is heated up and sensed by the thermistor NTC. The resistance will change, which from the theory, the higher the temperature, the lower the resistance. Thus, the non-inverting amplifier will convert the change in resistance to voltage. Then the voltage will display on the blink app. For the comparator, the LED will be bright if the amplified voltage from the non-inverting amplifier representing the temperature is higher than the reference voltage of 2.45 watts set at the threshold of 38 degrees Celsius. When the temperature exceeds this limit, the comparator output goes high, activating the LED and providing a clear visual indication of a high fever condition. On the other hand, if the amplified voltage is lower than the reference voltage of 2.45 watt, indicating a temperature below 38 degrees Celsius, the comparator output remains low and the LED will not be bright. This condition signifies that the temperature is within an acceptable range and there is no high fever detected. Now I'm going to present on the first part of our instrumentation system, which is NTC thermistor sensor. The thermistor sensor is a type of temperature-sensitive resistor that changes its resistance with temperature variation. It is typically placed in contact with human body to measure body temperature. As the body temperature changes, the resistance of the thermistor also changes, leading to a corresponding variation in voltage output. The thermistor serves as the primary temperature sensing element in the system. The next part of our instrumentation system is operational amplifier. The non-inverting amplifier is an essential component in the system responsible for amplifying the voltage signal produced by the thermistor sensor. The amplification process ensures that even small changes in temperature result in significant changes in voltage, thus increasing the system's sensitivity to temperature variation. The gain of the non-inverting amplifier can be adjusted based on specific requirements of the application, allowing for precise temperature measurement. The gain of non-inverting amplifier is 2. The non-inverting amplifier configuration involves connecting the thermistor sensor's output to the non-inverting input terminals of the operational amplifier. This setup results in positive feedback, which means that the output follows the non-inverting input but amplified by the gain determined by the feedback resistors. The next element is comparators. The comparator's use is LM324N. The comparator is a critical electronic circuit that determines whether the body temperature exceeds 38 degrees Celsius, the predefined high fever threshold. It compares the amplified thermistor voltage from the non-inverting amplifier with a reference voltage set up to 2.45 watt. When the amplified voltage is higher than the reference voltage, the comparator's output goes high, with the logic level of 1, automatically switching on the LED light to indicate a high fever. If the voltage is low, the output remains low with the logic level of 0, and the LED bulb remains switched off. In our project, the comparator plays a vital role in controlling the LED, providing a clear visual alert for temperature higher than 38 degrees Celsius. It efficiently makes a binary decision based on the voltage comparison, effectively activating the LED when detecting a high fever. The comparator ensures precise LED activation, making the system reliable and responsive in monitoring high fever conditions. The fourth part is Arduino Wi-Fi to Blink. The Arduino Wi-Fi board is equipped with Wi-Fi capabilities, enabling it to establish a connection with the Blink mobile application. The Arduino processes the amplified thermistor voltage and the temperature data and wirelessly transmit it to the Blink app. The Blink app acts as the user interface, display the real-time body temperature reading on the plot. Users can monitor temperature changes continuously and track fever patterns over time. The VMOS D1 Wi-Fi development board is an excellent component selection for designing an instrumentation system based on thermistor transducer for temperature measurement. The Blink app allows customization of plot graph settings such as time intervals and temperature scales to tailor the display according to individual preference. The flexibility enables users to focus on specified period or temperature range, aiding in the accurate assessment of body temperature fluctuations. Furthermore, the Blink app data logging functionality allows users to export temperature data for further analysis or to share with healthcare personnalists. The features is especially beneficial during medical consultation, enabling informed discussion based on comprehensive temperature records. The last component of our instrumentation system is LED indicator. An LED is used as indicator to provide a visual alert when the body temperature reaches a high fever level, which is set at the temperature of 38 degrees Celsius. When the temperature reaches this threshold, the LED bulb will light up, indicating the presence of a high fever. When the temperature is below 38 degrees Celsius, the LED bulb will switch off.
Hi, my name is Vincent Yuan. Now I'm going to present the functionality demonstration. When our device is connecting on the Wi-Fi, now we can open the mobile apps and select the temperature, and now it shows the temperature that received from the sensor on lifetime. And when our body touching the sensor will receive heat and the temperature will start to increase, which is shown on the Blink apps. After that, when the temperature is high above from 38 degrees Celsius, the LED will start to light up, and it shows that our body temperature now is too high. And this is our group presentation. Thank you for watching.